range expansions, adaptation, and expansion load. So hopefully you're all familiar with at least one range expansion that is for humans expanding out of Africa. But there are many other examples of range expansions, especially if you think about temperate species having recolonized post-glaciation, or if we think about climate change, we may expect range expansions to become even more prevalent in the future. Okay, but so before I get into the meat of the talk, I have to go through a few definitions so that we're all on the same page. The first one is expansion load. And so we define expansion load as the reduction of fitness due to the expansion process. So what do I actually mean by that? There are some cool population genetic processes that go on during range expansions, namely gene surfing or allele surfing. And so this happens because if we have a species range over space, and we look at populations at the range edge, they're often of lower density, so they have smaller effective population size. Smaller effective population size means there's more genetic drift, and selection is less effective. On top of this, these small populations serve as the source of founders for future populations as the range expands. So those populations are undergoing repeated bottlenecks, repeated founder effects, and they're having reduced genetic diversity. So if we look at a schematic of this through time, we follow these red and green alleles over space, and now at our range edge at T2, we have red allele is increasing in frequency. If we go a little further, we see that this red allele is now actually fixed locally at the edge. Okay, and so this can happen to neutral alleles, this can happen to beneficial alleles, and this can happen to deleterious alleles. And when this happens to deleterious alleles, that's what we call expansion load, because this fitness reduction accumulates at a range edge. And so a lot of work has been done looking at this, namely by Stefan Feischl and Laurent Escoffier, where they've shown severe fitness reductions at range edges due to this accumulation of deleterious alleles. And this has also been posited as potentially a reason for genetic diseases we see in humans that have accumulated as they've expanded over space. Okay, so we'll move on to the second key definition, and that is migration load. So migration load is a reduction in fitness due to immigration of maladapted alleles. And so what do we mean by this? There's also been a lot of work on this topic. Mark Kirkpatrick and Nick Barton, as well as Jacob Polikova, have done work looking at how populations locally adapt over space. So if we have an environmental gradient shown by this blue line here, and our population in orangish yellow existing on it, locally adapted to its current location in space, they've shown that on shallow gradients, populations will continue to expand and adapt to new conditions as they spread across this range. However, if we make that gradient much steeper, populations near to you are so much more differently adapted that when migration happens, you become locally maladapted. This can lead to local extinction and your range can contract. So a lot of these processes have been investigated why range limits might be forming. Okay, so what we're doing for our project, though, is looking at the combination of these two processes. So they've never been looked at together before. So we're seeing if local adaptation at range edges can be reduced by migration load and expansion load. And we have two sort of a priori hypotheses. The first might be just that these two processes combine to make fitness worse overall at the edge. Or maybe the second one is that they interact in some way to change the effect of each other. So to get at this, we did individual-based simulations forward in time using the program NEMO. We simulated hermaphrodites across a large-scale landscape. We gave every individual one quantitative trait with 100 loci. This quantitative trait is what determines your level of adaptation to the landscape. And then every individual has the potential to have up to 1,000 deleterious alleles. And so all of these loci were randomly distributed across the genome in each simulation. Okay, so the quantitative trait adapting to the landscape, we did 3 different types of landscapes. One was just the absence of a gradient. One was a weak gradient, so shallow. And one was a steep gradient, so strong. Okay, and then so for the deleterious alleles, again, there are 1,000 of these. They're biallelic. If you mutate at one of these loci, it's unconditionally deleterious, regardless of where you exist on the landscape. We did 3 genome-wide deleterious mutation rates. First, just none, then 0.1 and 1. We gave every individual a potential for fast mutations, and then we did a gamma distribution of effect sizes for these loci. So we tried to make this distribution of effect sizes as realistic as we could based on what we know of biology. So that looks something like this. It's a leptocritic gamma, and then we also gave 3% recessive alleles within those loci. Okay, so what this looks like when we actually put the simulations in action, we have this large-scale landscape. Individuals start at the left, and then they just expand over empty space. Any given spot on the location has a defined dispersal kernel that says the probability of you dispersing a certain distance. And then there's a smaller breeding kernel that defines your probability of mating with nearby individuals. Okay, And so when we look at the results, we measure a few things. The first is the speed of expansion. And so to do that, we defined an explicit range edge, which we define based on the first point in the landscape where population density drops to 50% of what it was in its equilibrium in the core. And so then we track the movement of that range edge over space to see how fast expansion proceeds. Then we also measured fitness at both the range edge and in the core. And so to do that, we included individuals at that same 50% point, but also further out to the actual end of the range edge. And then the core is just the furthest left point within the landscape. And so because we have this simulation approach, we can split apart total fitness into our two components that we modeled, so the quantitative trait adapting to the landscape and the deleterious alleles. So I'll go through the results first for the quantitative trait. So if we look at that, we have the fitness on the y-axis here. We have our three different deleterious genome-wide mutation rates in each panel, and then within a panel we have our three levels of gradient. And so the first point here we see is that if we compare the core, so the solid points, to the range edge, we see that having the presence of a gradient reduces fitness at a range edge. The steeper your gradient is, the more severe that reduction in fitness is. But we also see something else interesting where if we increase our mutation rate for the deleterious alleles, so we have more expansion load going on, we see that you're not as severely maladapted at the range edge, so your local adaptation is a little bit better as you increase mutation rate. So to look at this further, we go ahead and look at our deleterious mutations. And so results for our expansion speed, and that seems to explain what's going on. We see that in the presence of an environmental gradient, the speed of expansion is severely slowed. And so that makes sense. The steeper your gradient is, the more difficult it can be to locally adapt. It takes more time to spread across the landscape. And because it takes more time, this process of expansion load is alleviated, so you have more time for evolutionary rescue. So migrants from the more dense region of the species range can migrate to the edge, introduce beneficial diversity, and sort of halt that fixation of deleterious alleles that may be accumulating. So that's very cool. And then just to briefly explain that other interaction we saw where more expansion load caused less maladaptation at the range edge. That's a little more simplistic, so I'll just show you a snapshot in time of fitness. So the only thing I want you to take from this is that we have our fitness components for the quantitative trait in blue. So this is just looking across a landscape at one point in time for all our replicates. So blue quantitative trait fitness, in red is fitness for deleterious alleles. And because total fitness is just the product of these two, to even exist, the product must be above some certain level for populations to persist. So as you add more expansion load, so if this red lines get lower and lower, the blue line has to go up higher. So that's why we see less maladaptation at the edge when we have increased expansion load. So just to sum up, the take-home point is basically that expansion load and migration load do interact to impact local adaptation at the range edge. When you're more locally maladapted to an environmental gradient, this reduces the speed of expansion, and this slowed down speed of expansion allows for more evolutionary rescue, allows for more recovery from expansion load. So maybe this might have implications for studies of looking at expansion load in humans or other species as we look at range expansions happening in the future. And with that, I'd be happy to take any questions.